I want to just point out a couple of things about these variables. None of these are any big deal. We know what displacement is, we know what velocity is, we know what acceleration is, I hope. Before I go on, though, I do want to make this point about the equations and an assumption that they make about the displacement. The displacement is assumed to be the displacement from the equilibrium position. Everybody got that? So where we had that horizontal line drawn in the diagram last time, that is the zero position. So if I back up one slide here, to this slide, this horizontal line that we had on our diagram right here, that's the origin. Above that is up, below that is down. I don't care whether you define up or down as positive, it doesn't make any difference to me. Okay, and it really doesn't make much difference for using the equations. Everybody good with that part? Any questions about this so far? Doing all right?
Will you always tell us what equilibrium is, or can we choose?
Equilibrium, no. You cannot just choose it. Equilibrium is always the position where, even if the mass is moving, if it weren't, it would hang at rest. So when we did our diagram last time and we had the spring force up and the weight force down, and those guys were equal and opposite, they have to be, that is the equilibrium position. And that is also our origin. That is always where we put the zero displacement point. Everybody good? All right, now that having been said, what's the period? Adrian, the time for what? Okay, the time it takes to get back to the equilibrium point. Okay, so I'm going back to my diagram again. We need to be kind of careful with that, because here's our equilibrium line again. Okay, that will do. Okay. There's our equilibrium line. Everybody good? Here's the thing. You already have in your notes that at time 1, because the net force is 0, the acceleration is 0, right? And the displacement is 0, right? 0, not 0. There we go. Everybody got it? No big deal there. Here's my question for you, though. At time 1, what is the direction of the velocity of the mass? Up. At time 3, what is the direction of the velocity of the mass?
Down.
Down. Because of that, the time interval between 1 and 3 is not a full period.
Is it the period between 1 and 5?
1 and 5 is a full period. Here's how we define a period. A period is the time required for the motion to completely repeat. And by completely repeat, I mean the velocity has to be, or the displacement, let's start with that. The displacement has to be the same, the velocity has to be the same, the acceleration has to be the same. Okay? 1 to 3, yes for displacement, yes for acceleration, no for velocity. 1 to 5, displacement, velocity, acceleration, all match.
Period is the time it takes for what to complete?
The motion to repeat.
The motion to repeat completely. So it means displacement, velocity, and acceleration all have to come back to their original value. How are we doing?
Fine.
Everybody okay?
Yes.
Looks like a sine wave.
It is a sine wave. There's a reason for that. Oh no. So continuing with this, for reasons that are completely beyond Mr. Lines, I never see this equation in a textbook. I don't know why. But let's make this clear right now. The period, we use a capital T because it is a special time interval. It's not just any old time interval like a delta T. And it's equal to the time that passes divided by the number of oscillations. Okay? What's that? For, no, not that I know of. Doesn't mean there's not, but it's definitely not one I know of. Now, that having been said, period is the time per oscillation. What are the units for period?
Seconds?
Seconds. Okay, so our units here are seconds, and really it's seconds per oscillation. Remember how annoyed I was earlier that we didn't write down radians? We don't write down oscillations. I'm still annoyed with that. I'm just like, what? But nobody's listening, so.
Can you fill out a petition or something to like change this?
It's called intellectual inertia,
Mhm.
and basically you have to overcome the habits of all the old white guys that have done all this research.
Well, you're never gonna change the habits of old white guys.
Yeah, I mean, we're done, exactly.
Yeah.
All right, see, which is why even though I'm annoyed by it, I don't write down oscillations either. What's frequency?
1 over 2.
Right, frequency is the inverse of period. So frequency is equal to the number of oscillations divided by the time required for those oscillations. What are the units for frequency?
Inverse seconds?
Inverse seconds. So you could write it this way. You can write it as oscillations per second, but we don't write the oscillations, so the units are per second. However, this shows up often enough where we actually almost never write that for the units. What are the actual units we use for oscillations per second? Andre? Hertz.
Whoa.
F. That's an F. It's not a Z. How do you get Z out of that? There. Yeah, the Hertz, that's a Z. All right, I'm about to continue if we're good. Everybody okay? All right, so we are going to, I'm going to have us escape from this for a moment. And we're going to take a virtual field trip.
What's his name?
Let's go to Nigeria, bro. Let's go to Nigeria.
Why did you use cyberbullying on Twitter yesterday?
Alexa started it.
Honestly.
Sí, girl. Sí, del caso. It's like in Spanish. I was like,
Acoso. Huh? Yeah, don't worry about it. Just get them to having Twitter.
All right, there's way too much talking. I want everybody
I'll show you
to stop
later.
for a moment, and I want you to watch what's on the screen. If you cannot see what's on the screen, you're sitting in the wrong place. Let me give you a little bit of explanation about what it is you can see on the screen. The first thing is this. We have a mass on a spring in blue on the upper right. Everybody good? We have a mass on a spring oscillating horizontally in yellow at the bottom. And then finally, this is a wheel that's going to rotate, and you'll be able to tell how fast it's rotating because this dot is a point that's been marked on the wheel. Everybody okay with all of that?
Yes.
So, that all having been said, here we go. We're going to start the masses oscillating.
Oh,
Now, the guy that wrote this simulation did a really great job because one of the things you can do with this is you can take the wheel and you can change your point of view. So we're going to change it so that we're watching the face of the wheel to watching the edge of the wheel.
Whoa, what? Whoa. What's the purpose of viewing the edge of the wheel?
So, the purpose of viewing the edge of the wheel is now as you watch the dot on the wheel as it rotates, you can only see the vertical component of the motion of the dot. The horizontal component has been eliminated.
Oh.
Now that we're watching only the vertical component of the motion of the dot, look and see how that compares with the motion of the vertical oscillator.
It only cares about the vertical motion.
It's the same thing.
Component.
There we go. It's exactly the same thing. It only cares about the vertical motion. The vertical oscillations are exactly the same as the vertical component of rotational motion. In other words, let me put it this way so it's even more general. Simple harmonic motion is a single component of rotational motion. In other words, the displacement for a vertical oscillator is the vertical component of the displacement of the dot on the wheel. Sure, the displacement of an oscillator is the same as the vertical component of the displacement of a point with rotational motion. Now I'm going to reset this so that we can see this from the side again. And we can also do the following. We'll let it start. Note, I'm just going to let it run for a moment while I talk about it. On the right-hand side, the graph you see being created, the sine function graph, that is a position versus time graph. The red arrow that goes along with that, the length of that arrow represents the magnitude of the velocity of the oscillator. When the oscillator gets all the way down to the bottom, notice the arrow disappears, and we're back. Disappears, and we're back. The arrow is its largest at the middle, and then shrinks down to 0 at the extremes. Everybody okay? All right, I'm going to pause the whole thing, which is also a cool thing you can do with this, so we can look at it in a little bit more detail here. Yeah, about there. That's good. Everybody okay? Now, a couple of things here. Looking at this, that I've done a really nice job with. If you look at the point on the circle, okay, the blue arrow represents the vertical component of the velocity of the point, which is also the vertical component of the velocity of the mass. Note, this arrow right here and this arrow right here will always have the same length. Everybody good? Any questions about that? Okay, and let's see here. Erase all strokes. Let's also note the following. This distance, I'm going to use something a little smaller here. This distance from equilibrium to the maximum displacement right here that I just marked in yellow. Anybody know what that's called from your reading?
Amplitude.
That's the amplitude. Here's my next question though. On this diagram, where else can I find the amplitude other than where I just marked it? What?
The radius of the circle.
The radius of the circle. The radius of the circle is also the amplitude. So this, yeah, I'm going to go to the pink color here. This, which is the radius, is also the amplitude of the motion. Everybody good? All right. Take a deep breath. There's no crying in physics class. This angle, let's see here. I want another color. Green would be good. There's no green on this. I could use green. This angle right here, that angle represents the angular displacement of the mass from the beginning. Let me say that again. Brandon's like scrunching up his forehead and stuff, and I get it. That angle represents the angular displacement of the mass from the beginning. Everybody good?
Where's the beginning?
The beginning in this case is right about here. Stop that. Right there where I just marked in green, because that's the last time the mass passed equilibrium on its way up, which is how this whole thing started.
So what's the theoretical mass that we're displacing in this illustration?
What do you mean by what's the theoretical mass?
Well, because you're saying that angle, right, is the angular whatever.
Here's what I'm going to need to do. Hang on for a moment. We can do this.
I guess my question is, why would there be angular displacement on the vertical?
Just a moment. Okay, we're back to pretty much what I had on the screen earlier, but not exactly. And the reason it's not exactly is because I added a few more oscillations so that we could look at them. Here's what I want you to recognize is going on over here. What is this? Yeah, this is a sine curve.
Good job.
Actually, it's a sine curve because it starts right here.
At the equilibrium.
Everybody good? Everybody good with this?
Yes.
Are there any questions about that? Note that when the mass has gone from the point I circled, which was the very beginning, to this point, it's completed one full oscillation. Good? Okay. Deep breath. How far has the dot on the circle traveled during that time interval? The
2 pi
circumference.
radians.
That's the linear distance, right? What's the angular displacement of the dot in going from the first point I circled to the last point?
2 pi radians.
2 pi radians. What we are doing is we are dividing the motion of the oscillator up into 2 pi radians, because it matches the motion of the dot. So this angle that I'm marking right here, that angle, does everybody see where I marked that? Okay, this angle, that represents the angular displacement of the mass from when it was right here to when it got right there, which is where we stopped it. How are we doing? Everybody good? Now remember that this side of the triangle we've got over here, the radius of the circle, is also the amplitude, right? And this side of the triangle, new color. Yeah, we'll stick with the green. This side of this triangle is opposite the angle I have marked, right?
Yeah.
Everybody good? And it also represents the current displacement of the mass. Let me say that again. I want to make sure everybody's got this. This hypotenuse here, which is the radius, represents the amplitude. This other side of the triangle I've got marked in green, which is opposite the angle I've marked, is also the current displacement of the mass. Everybody okay? So I can write an equation which says, I know, oh no, now there's going to be equations, which says that the sine of the angular displacement for the angle I marked, and actually I'm going to do this, hang on a second, instead of angular displacement is just theta, I'm going to mark it as delta theta. Okay? Sine is equal to, okay, this may hurt just a little bit. You're going to have to remember all the way back to trig. Sine of an angle equals the opposite side, which is the current displacement over the hypotenuse, and the symbol we use for displacement is a plain x, and the symbol we use for amplitude, which is the hypotenuse, is x with subscript 0. How are we doing?
That's for amplitude x subscript 0.
Yes.
Brandon's face.
I didn't do it.
Why?
Explain me.
That's so dumb.
Hey, you guys were the ones that were giving me a hard time the other day about not using the symbols on the formula sheet. This is the symbol from the formula sheet. A little rearranging will give me that the current displacement equals the amplitude times the sine of the angular displacement. Everybody okay? Patrick, why are you shaking your head no?
Because I thought this was a fun visual.
Sorry, I didn't say we were going to have fun on the virtual field trip. I said we were going on one. And I didn't say, would you like to go on one? I said, come on, we're going. All right, continuing with this. Reminders from your composition notebook. Angular velocity, which is the same thing as the angular frequency.
Say again.
Let me say that again. Angular velocity, which is also here what we call angular frequency, is just equal to angular displacement over time. Everybody all right?
Bless you.
But hey, if we rearrange that, the angular displacement equals the angular velocity of the dot, which we call the angular frequency for the mass, times time. And I'm going to drop the delta because it's not going to show up later on anyway. I wish it did. It bothers me tremendously that it doesn't, but okay, I guess I can live with that. So I can rewrite this and say the displacement of the mass as a function of time is the amplitude times the sine of the angular velocity of the dot, or the angular frequency of the mass, times time. Lacey's giving me a strange look. How we doing, Lacey? Just okay in terms of the math? All right, so let me talk about angular frequency for a moment. Everybody hang on. Frequency. Let's go back to frequency for a minute. We had frequency equals the number of oscillations over the time interval, right? So let me rewrite that. First this way, frequency equals one oscillation over the period. Because the period is the time for one oscillation. Good?
Yeah.
But how many radians for one oscillation?
2 pi.
2 pi. So if I want to write the angular frequency, it's going to be equal to 2 pi over the period. And that will give me an answer that we only write as hertz, but really it's radian hertz. We just don't write the radians just to drive Mr. Lyons insane.
That's basically the same formula as the one in pre-cal, 2 pi over the absolute value of b.
Yeah,
It's
it
the
is.
same thing.
Colin, you got a question?
Is there a symbol for angular frequency?
Yeah, the same one as angular velocity.
Oh.
Yeah, so we still use the omega. Well, they're both radians per second. A radian hertz is a radian per second. Okay? Everybody good? More or less? Is that helping any, Lacey? I hope. Sheridan? That is omega. Same as angular frequency. Or same as angular velocity.
So is the omega equals is that just the same as the other one where it's
Same omega. Everybody all right? Okay. Delta theta stands for the angular displacement, which is the angle I've got marked right here. I'm not going to write it on the screen because, well, actually, let's see if I can manage that. It's this angle right here that I just put the theta on. Right here. That angle is our delta theta. I'm not going to try and put a delta with it. It's just too small. I don't have enough space. How are we doing with that idea? Everybody all right? Okay. So, I think we should learn a little calculus.
I'm down.
We can? Okay, good. We're jumping ahead a little.
No, I still
Everybody's got this part?
Have you ever learned this?
Unless we're proving trigger identities in here,
That.
I don't wanna hear it.
And we're going to go back over here.
We're starting simple and isolation. She's like, I don't understand. So we did it before.
And we're going to go back over here. We're going to bring this up.
Not Q, not P.
It like says like it's right hand side of the whole school.
So I'm drawing
A contrapositive, if P then Q, that means if not Q then not P.
position in meters
Let's go.
versus time in
I'm still abused
seconds
of logic.
graph for the simple harmonic oscillator. We'll do this in a nice Starling fold. Okay, what kind of a graph do we have there?
Sine
Huh.
curve.
A sine curve, okay. So here's my next question. So bright last Adrian. Here's my next question.
Oh my god, stop.
Where on this graph can we find the velocity of the mass?
What is the y-axis thing?
There we go, the slope. The y-axis is x in meters,
Oh, that's.
and the x is t in seconds. So the slope of this graph will give us the velocity, right?
Yes.
So now I'm going to make another graph down here, v in meters per second, versus time in seconds. Okay? And what I want to know first, or next, let me see here. What I want to know next is I want to know about the slope of the position time graph right there at the point I just marked in pink.
0.
Now your choices are this. Your choices are positive, 0, or negative. That's it, to make it easy. Okay? So what is the slope at that point?
Positive.
No,
It's
it
definitely
is
positive.
not 0.
Positive.
Reminder that the value of the position is 0, but not the slope of the position time graph. The slope we can get by drawing a tangent line, right? Okay, the slope of the line I just added is
Derivatives.
positive. So that means the velocity
Are you
value
gonna take
has
H
to
on this?
be
Are you gonna take H on
positive
this?
to times 0. So I marked the velocity value right here. Everybody good? Okay, new question. What is the slope of the position time graph at the new point I just marked in pink? Let's see here, who to pick on. Annie? What's the slope at that new point? Yep, right at the top. Horizontal, so 0, exactly. If we draw a tangent line, it's horizontal. So whatever we can say about the slope of the position time graph is true about the velocity. So we are now down to 0. There's our new point. So now I want to know about the slope at this new point where the graph on the position time is crossing the axis again. So, Richard, what's the slope there? Positive, 0, or negative? Negative. We draw our tangent line. It's negative. So here's our point right here. Cut it out. I don't have time. All right, so let's see here. Daniel, what's the slope at the point right there at the bottom? There we go, 0 again. So I'm going to mark my 0 point over here. Okay, and then finally, let's see here. Patrick, slope right here, positive, 0, or negative? Positive, there we go. So we have a positive value here. And when we draw our line to play connect the dots, we get a graph that looks
I think
like
mine is
this.
a lot more pretty.
What kind of a graph is that?
Mhm.
Cosine, yay! So listen carefully. A function, listen, don't write, listen. A function that describes the slope of the sine curve is the cosine function. Good? Which means if the position versus time graph is a sine function, the velocity versus time graph will be a
Cosine.
cosine function.
So this applies to every graph that happens to be a sine function.
Yes,
The graph of its slope would be a cosine
every time,
every time? Okay.
guaranteed. Everybody good? Okay, well, we're running out of time, so I gotta speed things up here now.
Oh, God.
And by the way, listen, if we repeated this for acceleration versus time, you would find that the graph was the negative sine function. Okay? If we graph the slope of this function, we'll get a negative sine function.
So it's just gonna be like,
Okay? Yep.
okay.
It would just be like this.
And then you can get into this.
And that's the acceleration. That having been said, hey, equation!
Good lord.
I don't even know, like.
You want? Where's your dad's formula sheet? Where do you think that's going? Okay, a couple very quick things. Because we are running out of time, I'm gonna do these pretty fast. Okay, so make sure you're paying attention and keeping up. What I'm gonna do first is I'm gonna assume t is 0. If time is 0, then Patrick, what do I get for omega times time? Great, Joanne, what do I get for the sine of omega times time? No. 0. Ashton, what do we get for the amplitude times the sine of omega times time? 0. What this all means is that we are assuming when we use this equation at t equal to 0, x was equal to 0. Now over here, where we use the cosine function, where t is equal to 0, x is equal to amplitude. Make sense? Now, if we come down here to our velocity equation,